In my previous recording, I told you that in general, L rotational and omega do not point in the same direction. It is true, though, that there are some cases where actually L rotational and omega happen to point in the same direction. It's just that in general, those two vectors do not point in the same direction. I'm going to show you what needs to happen for L rotational to point in the same direction as omega. If I want L rotational to be pointing in the same direction as omega, then I need to have a number times omega x for the x component. Okay, let's do this again. So L rotational is, this is the x component, that's the y, and that's the z. If I want L rotational to really point in the same direction, then that means that the x component of f of the rotational angular momentum needs to be a number times omega x, and Ly needs to be a number times omega y, and Lz needs to be a number times omega z. Okay, whatever number, let's say k, l, m. Okay, at this point I don't really care. They just have to be numbers, and this should be only omega x, this should be only omega y, and this should be only omega z. Now, if I take a look at my general result, then, sorry, let me go back. Of course, those numbers, okay, those have to be the same. All right. So if I go back and look at my general result for L rotational, to have an x component that only depends on omega x means that these two need to be 0. Okay, so I need to make this term to go to 0 and this term to go to 0. Similarly, for Ly, if I want it to be just a product of omega y, I need to make this 0, I need to make this 0. And for z, I will need to make this one and this one 0. Now, if I want to make this term and this term 0, then the ixy will have to be 0, and the ixz will have to be 0. Similarly, this and this term needs to be 0, and this one needs to be 0. But then, if you take a look, the only numbers that I have left as non-zero in the moment of inertia tensor are the diagonal ones. So if you choose your axis so that the moment of inertia is ixx 0, 0, 0, iy, y 0, and then 0, 0, I, z, z. if you choose your axis, the three axes, to be the ones that you need, then for those, it is possible to find three axes that will give you, three axes I mean x, y, z, it is possible to find three axes that will give you a moment of inertia tensor that is diagonal. In that case, if your angular velocity points in one of those three axes, then your angular momentum, your rotational angular momentum, will point in the same direction. Let me show you what I mean with that. So if you choose your the three axes that I talked about, your x, y, z, to be the special ones, the special set that we call the principal axis, then if your angular velocity vector is omega x 0, 0, then I times omega, so I'm multiplying this 3 by 3 matrix with this 3 by 1, it's gonna give me Ixx times omega x 0, 0. And this is equal to L rotational. So now you can see L rotational, the x component is a number times omega x 0, 0. So in this case, omega, if omega points in the x direction, L rotational points in the same direction. So for that, and the same is true if omega is 0, omega y 0, you will find L rotational to point in the y direction. So for if you do use the three axes that we call the principal, the three principal axes, then you get a moment of inertia that is diagonal, and if omega points along those three, along one of those three principal axes, your L rotational will be parallel to your angular velocity. Only if you use one of those three principal axes for your angular velocity vector.